This video is a continuation of the previous video on RF monitoring or sampling circuits. If you have not watched the previous video, a link to it is provided below, and it should be viewed prior to watching this video. The previous video discussed the desire to have a circuit which could monitor an RF signal both in the time and frequency domain and do it in a manner that would not be intrusive upon the circuit that we were monitoring. 7 circuits were provided as possible candidates. There may be more. If anybody has some suggestions, please let me know. But the 7 circuits that I came up with are shown here. The previous video analyzed these 4 voltage monitors and discussed the relative merits and weaknesses of those. This video will continue on and analyze the current monitor and a couple of power monitors. The voltage monitoring or sampling circuits that we looked at in the previous video all had a similar requirement. The component that we were using to sample the signal was a shunt component, and it needed to have an impedance that was very, very high in comparison to the circuit we were trying to monitor, resulting in a negligible effect on that circuit. We have a similar requirement for the current monitor. In the current monitor's case, we need to have the monitoring element of the current have a very, very low impedance compared to the impedance in the circuit so that we don't affect the circuit itself. Additionally, the current that we have flowing in this circuit is not referenced to ground. Consequently, we need some way to get our output signal back to ground, and a transformer is the device that does exactly that function. Looking at this circuit for a moment, it may seem to be complicated more than necessary, but we basically have a transformer where we have a single turn going through a core here. We have some larger number of turns here. We have an impedance here and another impedance. We probably don't need R2, but if you want to tweak the actual value of the coefficient of coupling, R2 is a valuable component to have. And the impedance that the line sees here is the inductance of one turn, which is A sub L, in parallel with this impedance in parallel with those 2 impedances added up. So it's the 15 ohms in parallel with 84.8 divided by the turns ratio squared, and that's the basic way it works. However, there's a lot more to the circuit than that, but let's just keep going for a moment. We set this resistor up, which is the one that has the most effect on it, on the impedance. It's 15 ohms, 15 turns, 15 divided by 15 squared is about 1/15. So this is about 0.06 ohms. 0.06 ohms in a 50 ohm circuit has an effect that's I'm going to consider to be negligible. So let's look at the resulting circuit, the results that we get from our circuit here. The first thing is we see a coupling factor that's very, very close to 40 dB, minus 40 dB, and it's flat with frequency. We also see an SWR that looks very, very good. It's not 1-to-1, but it's way less than 1.05 to 1. We do that with the same circuit, same equations we did before. To measure the coefficient of coupling on the circuit, we look at the 10 times the log of the ratio of the powers between the power in our device that we're using to measure divided by the power in the output. L sub P is this power. And we come up with 40 dB, so we see 1/10,000th of the power. That's all. This is good, and this is much better than most of the voltage monitors that we looked at before. But let's continue on. We discarded those circuits early because they had faults. So far, this circuit looks to be pretty good. The next thing we want to do with the circuit, though, is look at the power in the circuit. The resistive circuit that was a voltage monitor looked pretty good, too, until we looked at the resistors and saw that we had 20, 28, or 29 watts with a 1500 watt source. So, again, I plotted all those powers here. Let's look at them. And what we see is a little less than 1.5 watts in R1, which is across the transformer, and then R2 and R3 are down in the 1 or 2/10ths of a watt range. So this total power here is actually less than 2 watts. 2 watts is much, much better than the 29 watts and is perfectly acceptable to have in a small little box. We could also measure this power another way. This is kind of getting off topic, but let me digress just for a quick moment. And we can look at the power right here, the power at U1. SimSmith has two types of power it measures, and it measures each type in two different ways. An up arrow next to the W means the power in the component. And the power in this component, since it contains both these two resistors and the load resistor, shows to be 1.72 watts. But if we were to use this type of a power, we're seeing the power flowing into the circuit. In that case, it's 1.5 kilowatts. So if you're using SimSmith and you get a result that seems really weird sometimes, look at the case of the arrow here. The arrow, this is kind of an interesting little addition to SimSmith. It's really nice, but it doesn't really tell you what it's doing. You kind of need to know that. Anyways, continuing on, we find that the power in this circuit is very, very good too. So what else can we do with the circuit? Well, anybody who's built any kind of RF circuits knows that a coefficient of coupling of 1 is nowhere close to being right. We may be able to get 0.96, 0.95, 0.97. We're not going to get 0.99 probably. We might get close to it, but not 0.99. So let's drop this off and see what happens. And while I'm dropping this down, watch this line right here. So as I drop the coefficient of coupling from perfect to 0.99 to 0.98 to 0.97 to 0.96, what we see is the coupling factor here dropping, but it still is remaining flat with frequency. We can easily adjust the value of this with a little tweak on the resistors here. So that's not a big deal. That's an easy thing to do. We see the SWR coming up, and what we're seeing with the SWR coming up is the leakage inductance that we see right here due to the incomplete coefficient of coupling. If we want to take that to an extreme, we can disconnect the secondary of the circuit right there, and here's the SWR that you see. And if we go and look at a point on this graph somewhere, and go over here and set the mode to be a series mode, we see 50 ohms plus 69 nanohenries. Well, 69 nanohenries is exactly what that inductance is. There is nothing shunning that at all with no coefficient of coupling. And if we connected this and we set this value to be 0, we get the same value we had just a minute ago. So as the coefficient of coupling starts to rise here, we set that, okay, that's good. As the coefficient of coupling starts to rise here, what we see is that the SWR starts to get better. And we see a rise in the overall coupling factor. So I'm going to leave this circuit maybe 0.98 for now. It seems to be pretty good. This SWR out here we can compensate for, as we've seen before with some components out here. So now this has passed another test. So what about the turns ratio? Is the turns ratio particularly important? And the answer to that is no. As we change the turns ratio to be a larger number, the transformer becomes harder to build and keep working nicely at high frequencies. As we make the number smaller, we start to see the power rise down here. Now, if we want to do that real quickly, we can set this to be, say, like 10 for a turns ratio. I'll drop this resistor somewhere around 10 ohms. This resistor will rise to 40 ohms to get the output to be right. I've done this too many times. Let's turn that off. We see a coefficient of coupling a little less than 40 dB. So we'd make this maybe, say, 10.2, and this would be like 38.8. And that's getting closer all the time. Let's just call that good enough. Now what we'll see in the resistor R1, where we had 1.5 watts before, now we're seeing 2.3. So we're seeing the power in that resistor rise. We have fewer turns on the core. I don't know what's a good. Both these would be perfectly acceptable to use. I'm going to go back to the original version. The original version is what I have built on some prototypes, but there's absolutely nothing wrong with. There's absolutely nothing wrong with doing the circuit with either. If you were to raise this to 20 or 25 turns, you'd find out that the current here, the power here would drop more and more and more and more. The downside to that would be that any coefficient of coupling here that has is less than 1 starts to hurt us more. So I'd leave the circuit to approximately, I'd stay in the 10 to 20 ohm or 10 to 20 turns range. And again, SimSmith's perfectly happy to analyze all this stuff. One of the things I mention it off and on in SimSmith, but one of the things that's really important is SimSmith gives us the ability to take every component we've got and just basically willy-nilly just change them and look at the results. That's something you can't do in programs like LT Spice where you have to go set a new test to run. And that's one of the huge advantages of using SimSmith for this kind of an analysis. So now let's look at what the real circuit looks like. Well, anytime you build a circuit at RF, it's never as simple as this. There clearly is a capacitance between this winding and this winding. And let's see what the effect of that would be. We could monitor, say, from the center of this winding to the center of this winding, and since that's one turn, it's going to be hard to get in there and do that. It's easier on a drawing like this to go here and put a capacitor, say, between here and here, and we'll call that half the capacitance that we'd measure, and then we put the same capacitor again on the other side. So if we had a circuit that had, let's just use an example, 1 picofarad capacitance between one winding and the other winding, each of these would be a half a picofarad. And if I put, and the circuits I've built, this overall number is less than a picofarad for the total when I've measured it. So let's say this is about maybe 0.3 picofarads, and this is 0.3 picofarads also. Now what we see is we see the coupling factor starting to change. It doesn't change a lot, but it's starting to change a little bit here. And let's look at that a little more closely. If we disconnect the ground side one, we see a little bit of change. But if we disconnect just the hot side of the secondary, we see almost no change. So capacitance here really doesn't hurt us. The capacitance here actually helps to balance out the SWR, but the capacitance here is the thing that hurts us. And that gets us to a point right now where let me take a little bit of a detour. Here's a pretty busy drawing. It shows 9 different ways to connect a transmission line inside a little box. The gray pieces here represent the walls of the box. The coaxial connectors are represented by these things that look like they have threads on them. And then I have a blue wire which shows if the center conductor of the transmission line is showing. Green if green is the shield. So in the first case here, I preserve the shield all the way through the connector perfectly. This works nice. This has the best SWR. It works the best, period. I can't do anything with it though. It just transfers the signal from here to here, and nothing can be seen or done with it here. Other ways we do it typically are at the end. It's hard to maintain the shield into the connector and solder this and stuff. So if you have the right kind of crimp tools, you can do it and stuff. But normally, a lot of times people will take a piece of transmission line and they'll take the braid and solder a little pigtail here and a little pigtail there. If we do that, we start to see that the impedance of this circuit is not as good as this circuit. Clearly, if we're not very careful and we make this longer, we get a poorer result than shorter pieces. And that should be pretty much obvious to anybody. And of course, this one here could have been done with 2 or 3 little pigtails. That would be better than one. But you know, I'm just showing some examples here. Here's a case where we do nothing but have the center conductor go across the little box. We rely on the shield current to come into the box, go around the box, whatever the size the box is, back up the other side, and back out. This will definitely be worse than any of these configurations in terms of SWR. However, as soon as we have a desire to put a toroid on our piece of transmission line, we have to put it on one conductor. If we go back to how transmission line works, at every single point in the transmission line, no matter what, say like right here, there's a current that flows on the inside of the shield and the outside of the center conductor. Those two are in phase and exactly the same magnitude. Any differences between those two manifests itself as a shield current on the outside of the shield. So here, what I just said is true. Over here, it's also true, but the value may be different. There's SWR on the line. We see a varying value of current. A varying value of current throughout the length of the line, but it also occurs on the shield and the center conductor at the same time. So, in this case, clearly we have a bit of a problem. We want the toroid here to work properly, which means we don't want to see the two currents balance each other out. So we put the toroid in this circuit. The shield current still flows around, does not go through the toroid. The center conductor goes through the toroid. And while a lot of SWR bridges are built like this, as you start to get to higher frequencies, the disruption of this circuit itself, this circuit has SWR. Even though it may be part of an SWR bridge trying to measure SWR, it has its own SWR. So if these two connectors are extremely close together, like almost on top of each other, we might get away with it. Otherwise, we do something like this. We bring our coax part of the way to the toroid, and then we maybe have a pigtail around it. Or maybe a little bit better than that, we bring our coax close to the toroid, and if the chassis is real nearby, we connect here, and then the path from the chassis back over to here is a lower impedance path than a little pigtail would be. Now here's a case that's interesting. A lot of SWR bridges are built like this. We take the transmission line through the toroid, but we can't ground over here. If you ground over here, then that represents the toroid doesn't see the current any longer. It sees the net effect of the two currents. So here we have a current in the center conductor. We have a current on the inside of the outside of the conductor, of the outside shield. And then that current comes out here, the shield current, and has to go around on the outside over here to ground. This current on the inside and the outside cancel itself out, and all the toroid sees is the center conductor current. And again, this has a little bit of SWR because once you get here, you have to go back over, you have to get back to here. You could even do it better than that. You could maintain the transmission line through the toroid. You could maintain it on this side up to a small gap and then have a complete structure that surrounded the toroid. That would even be better. But the point I'm trying to make here is if we want to measure capacitance from the center conductor to the toroid, we can measure it right here very obviously. Here, there is no capacitance from the center conductor to the toroid. It has been eliminated. What we see instead is capacitance from the center conductor to the shield, and then we see capacitance from the shield to the toroid, provided that this ground connection is very, very close to this and is a good ground connection. So, with that having been said, let's go back to the circuit again. We were in the process of looking at what this capacitance here did to our circuit, and we came to the conclusion that the one on this side really didn't affect it much, but the one on this side affects it a lot. So, if we put that capacitance back in here, and we see the signal, the coupling factor getting larger. This is less negative, so it's a larger coupling factor by a little bit. We could play the game where we put the center conductor through the toroid and came back and grounded it right away, in which case the circuit would look something like this. We have capacitance from the center conductor to the shield. We have capacitance from the shield to the one side of the transformer, and then we have some small impedance here at the center where the shield is to the actual ground of the circuit. This is not really the ground of the circuit. This is isolated from it by a little bit. So if we put some numbers in there, let's make L3 be like maybe, I don't know, 5 nanohenries for now. Let's ignore C2. So C1 now is a larger number than it used to be because it was 0.3 picofarads from here to here. By putting a shield in here and the thickness of the shield and all the other stuff, it's going to more than double. So let's make this about let's make it say 0.8 picofarads. And then this would also be 0.8 picofarads. Those two in series would be 0.4, where we had 0.3 before, now it's 0.4. And what we can see is all of a sudden we no longer have the change in coupling factor here. And as we make the ground get further and further and further away from the toroid, so that this path becomes higher impedance, we see it doesn't change much. So we have a pretty good way of negating this capacitance in this core. Now the circuit I'm going to show you did not do that. Here represents a close-up view of a current sampler that I built, which is built in built in the smallest die-cast box you can buy. That's easy to find. It's about an inch and an eighth wide. It's about 1 1/8 inches high, and it's a little less than 4 inches long. And this is a piece of 12 gauge wire between two Teflon SO239s. And here's my little toroid, which has 15 turns of number 22 gauge wire on it. Now you can't really see this, but there's a little circuit board on the other side here. The next picture shows the back side of that. Here's the toroid, and we're looking on this side. This is just a piece of single-sided printed circuit board, which I've taken a Dremel tool and I've ground out like this dog bone shape, and it's ground out here too. It's ground out down here also, so that I have I have two pads on there. I have a pad down here where the center connector of the output coax connects, and here's a connecting to ground on both two short paths. And here are the resistors that comprise the resistors across this toroid. In my case, it was 15 point something ohms, 49.9, 49.9, 49.9. These give me like 16.67 ohms. In parallel with 200, gave me something like 15.4 something, which is very, very close. Here's two stacked. These are 2512 resistors. They're good for 1 watt each. These are a couple 0805s, I believe, and they're 68 ohms, 68.1s, which give me 34 point something ohms. So this circuit represents pretty much what I've got in SimSmith in the ruse block. Here's another picture which shows this look maybe a little bit easier because I had it backlit. And this circuit has worked pretty nicely. I built several of these. Here's a little bit bigger picture of it. When I built this box, I took a piece of copper tape, bent it down around the sides, burnished it down real nicely. This is a single-sided circuit board that's soldered along the edge here, so it has very good connection to ground. And then I put nuts here, and I soldered the nuts to this, so they have very good connection to the ground here. And this circuit has worked very, very nicely. This piece of plastic is a fairly low dielectric constant. It turns out plastic is kind of an interesting material. You want an insulator in here, and this insulator that you put in here needs to locate the toroid. But in the process of locating the toroid, the plastic a lot of times has a dielectric coefficient of 4 or 5 sometimes. So Teflon is the best that we can generally come up with. But Teflon is not an easy material to make stick on wire and stuff. It doesn't stick to anything. But you can jam it in there, and it's good enough. Teflon will have a dielectric constant of 2.1. I use polyethylene a lot of times, high-density polyethylene, because it's available. It's really cheap. And it's got a dielectric constant of 2.2. So does polypropylene. But if we go to other materials, like this is a glass material, it's got a dielectric constant like 2.6. If we go to the common plastics like PVC, ABS, they're generally around 3.5. All these things increase the capacitance from here to these windings, and which makes our problem makes solving the problem a little more difficult. We could have, and I should have thought about this, I could have moved this circuit board in, notched it a little bit where the nuts are here, moved it closer, and used these wires to hold this toroid by itself. I could have dispensed with the plastic and just put a bare wire through the center. That would have given me less capacitance. As you can see here, I did not run the shield through here and back on the other side. This is a fairly short distance. I did not run the shield through here. The performance I got out of this circuit was quite good. The SWR at 150 megahertz was 1.02 to 1, and this helps. This little bit of inductance in here helps compensate for the SO239 connectors, and I'll go through that in a second here. But this circuit works really pretty nicely. And it's got a SWR, like I said, 1.02 to 1 at 150 megahertz. Its coupling factor at 100 megahertz was 40 dB plus or minus a tenth of a dB. And at 150 megahertz, it was 40 dB plus about 0.3 dB. Now, let's try to build a circuit in SimSmith that matches what I physically built. This circuit is my best guess at what I actually built without trying to take any losses in the core here into account or anything. A mated pair, an SO239 and PL259 pair that are both Teflon, looks like a transmission line that has a length of 1.03 inches, has an impedance of 36.2 ohms, a velocity factor of 0.695, which is the Teflon dielectric, and I gave it the same loss roughly as RG8. We have one of those on each end of our box, and then T3 and T4 represent the 12 gauge piece of wire that runs through the box. It looks like basically 0.4 divided by 12, or 0.4 inches long, of an impedance of 130 ohms, and I gave it loss half of what RG8 was. I don't know if that's correct or not, but the loss doesn't really change the problem much at all. In the middle, we have the circuit we were looking at before. This impedance is too low compared to 50 ohms. These impedances are too high. They do offset each other, and they offset each other in the correct direction, which is nice. I went and remeasured the capacitance on the transformer. I got 0.7 picofarads. It's tough to measure really accurate, really accurately small capacitances like this, but let's use 0.35 on each side. I built the circuit, used a 0.98 coefficient of coupling in the transformer, and all the same components as before, and I get a SWR at 150 megahertz, which is basic. Whoops, where are we here? Get the SWR curve. Sorry about that. SWR is 1.019. I said 1.02 for my circuit. And I had a coupling factor that was 40 dB minus about 0.4. This is 39.69. It's close. And this down here is just about 40, 39.95. This is not, my circuit's a little worse than this. My circuit's just a teeny bit worse than this. Pretty darn close though. So you'd say, wow, this is really good. I got a circuit that works really well. And the answer is it does work pretty well. I use circuits like this pretty regularly to monitor RF signals. They work fine. However, you also need to ask yourself a simple question, and that is, did I build what I really wanted to have, or did I build what I spec'd out to have? And when I lumped before the 7 circuits together, there were 2 distinct classes of circuits there. There were circuits that monitored voltage and current, and then there were circuits that monitored power. Monitoring power would mean anywhere you'd look in a circuit that had an SWR. So let's take this circuit for example here. 25 ohms. Now we notice, let's go back down to 14.1 megahertz here. We notice that we have 1331 watts output. There's a little bit of loss from 1500, and that's the mismatch loss due to SWR. We also notice at 1331 watts with 25 ohms, 2-to-1 SWR, at 100 ohms, which is another 2-to-1 SWR, we still have 1332 there, but whatever. They're basically the same number. And no matter what impedance we have here that would be a 2-to-1 SWR, we would see 1330 watts into the load. However, look at what the current sampler reports. The orange trace here, let me get rid of this. SWR is off the scale right now because it's 2-to-1. The sampler reports the power in the resistor here, R3, which is effectively the oscilloscope or the network analyzer, spectrum analyzer or whatever. It reports 67.8 milliwatts times 10,000, which would be 678 watts. It reports a value that's half as big as the real value. And in the case where it's 25 ohms here, it reports 269 milliwatts times 10,000, which is 269 watts, which is twice this value. And that is due to the fact that a 2-to-1 SWR has current that varies by a factor of 2, which is of power that varies. Effectively, if you say current squared is proportional to power, then that would be our 4x difference in power that we measured. All voltage samplers, all current samplers will have the same problem. A power sampler measures both, or samples both voltage and current, and it would report a number close to 1331 for all impedances that were a 2-to-1 SWR. So, did we build what we really wanted, or were we just successful getting what we spec'd? I kind of have some mixed feelings about that one. I knew it. I knew this was going to have this problem, but I built several samplers. I use them. They work fine. I try to use them always in a fairly low SWR environment. If we look at this and go to 50 ohms, and we see that the value here at 50 ohms is 1,500 watts. When you multiply that times 10,000, I'm going to go up to a 1.1 to 1 SWR, and it went to 1,380 watts, down again to 1.1 to 1 SWR, 1,660. That range is not huge, so if I keep the SWR under 1.1 to 1, this is a very useful solution and considerably simpler to build than an SWR bridge that can cover this frequency range. Kind of running out of time here, running out of energy on this video, so I'm going to do one more video and look at the SWR bridges as used as samplers and talk about a couple other ways that we could achieve the same kind of thing here. Thank you very much for watching the video, and I will do the other video very soon. I promise you part 3 will be the end.